Millimeter wave full duplex radios. As more and more people are using wireless devices in their daily lives, the data traffic demands is increasing by almost 50% every year, according to a recently published mobility report by Ericsson in 2020. Wireless researchers have tried to fulfill this increasing demand by using a two-pronged approach, that is, either by moving to higher frequency bands, which offer wider bandwidths and hence higher data rates, or by utilizing the existing frequency bands more efficiently and squeezing out more bandwidth from these bands using a variety of spectrum reuse techniques. In this work, we try to combine the best from both these approaches by enabling a spectrally efficient full duplex communication link at higher millimeter wave frequencies. Traditional half duplex radio either transmit and receive in two different frequency bands or in two different time slots. On the other hand, a full duplex radio can transmit and receive in the same time slot at the same frequency. This has the potential to increase the throughput by two-folds. Since a full duplex radio has to transmit and receive at the same time on the same frequency band, it suffers from the problem of self-interference, which is the transmitter signal leaking into the receiver. The self-interference signal is much more powerful compared to the desired signal arriving from the other radio. And this, in fact, is the challenge in the path of enabling full duplex communication, where one has to cancel the self-interference signal before decoding the desired signal. To cancel the self-interference signal, we use the signal model where the self-interference signal is essentially a transmit signal affected by the self-interference channel. The goal is to accurately estimate the self-interference channel and remove its effect from the received signal. While a lot of past work has been accomplished in full duplex at sub-6 GHz domains, we focus our attention at millimeter wave frequencies and demonstrate the first bidirectional full duplex link at 28 GHz. Since we have to cancel a huge amount of self-interference power, we adopt the approach of dividing our self-interference cancellation across the three stages of antenna, analog, and digital fronts. In the first stage of antenna cancellation, we leverage the small wavelength of millimeter wave frequencies to place a tiny strip of metal called the self-reflector symmetrically in front of the transmit and receive antenna. The goal of the self-reflector is to inject a negative copy of the self-interference signal into the receiver antenna so as to nullify it. What makes the self-reflector unique to the millimeter wave context is that it is feasible only at these small wavelengths. If one tries to replicate the self-reflector at lower frequencies, it will result in the size blowing up significantly, which will make it difficult to implement. In the second stage of analog cancellation, we use a custom RF chip, which provides us coarse grain and fine grain control knobs to quickly estimate the residual self-interference channel after antenna cancellation. In the third and final stage of digital cancellation, we observe that the baseband self-interference signal is affected by a frequency selective self-interference channel. To cancel the frequency selective self-interference channel, we divide our signal into many tiny time and frequency chunks and then estimate the self-interference channel for each of these narrowband time frequency chunks. At the end of the three stages of cancellation, we achieve almost 84 dB of aggregate cancellation across a bandwidth of 100 MHz, starting at 0 dBm transmit power. On the throughput front, we achieve almost 1.7 times increase in throughput compared to a half duplex link. Please visit our lab website to learn more about the project.